Okay, we start. Today we're going to talk about the Invitational Generator of continuous time Markov chain. Just a quick recall that in the last lecture we introduced what is a continuous time Markov chain. And we only focus on the continuous time Markov chain with the following properties. First, there's time homogeneity. Second, we only consider the right continuous process. And since our Markov chain only take value in the countable state space, this means that at each time, the Markov chain will stay there for a short time at least. And next, we require the process has no explosion. So it is either jump all the way, or it stay for some state forever, but it can't jump too much. Okay, the last requirement is the right continuity in the semi-group. So we require that the semi-group of the process, PT, it decreases to identity matrix as epsilon goes to 0. And today we will consider Invitational Generator. And in fact, what is this mean is we want to take derivative with respect to T for the semi-group. Okay. So first, a few more words about the semi-group. The semi-group we are considering is the right continuous. And we already know that this semi-group starts with identity matrix. And it has and for each T, this is a stochastic process, stochastic matrix. And we have a multiplicativity of this process. So P T plus S equals PT times PS. So here are just the three matrices, and here just the product of two matrices. And the last, we require that this right continuous process, the process is right continuous. So we require that as epsilon goes to 0, this matrix converges to identity matrix pointwise. So for each entry, it converges to identity matrix. And just one more word is combining these two facts. In fact, we know that this semi-group is right continuous at every time t. So it is right. So here we just assume that it is right continuous at 0. But since we know that we have multiplicativity of this semi-group, so combining these two, we know that we have right continuous at every point. Okay, so this is the semi-group. And the first theorem says, if we assume such semi-group is right continuous, then it tells us, in fact, we can take derivative. So the derivative exists all the time. So the theorem says, suppose PT is a right continuous semi-group. First, for the diagonal term, we know that it will approach 0, it will go to 1. So if we subtract by 1 and normalize by epsilon, then there exists a limit. So the limit exists. And second part, for the term of the diagonal, so for distinct states x and y, we know that this p epsilon xy will converge to 0. And if we normalized by epsilon, then the limit exists. So this theorem roughly says, as long as we assume the semi-group is right continuous, then we can take a right derivative. Okay, proof. So for the proof of the first item, we need the following lemma. So the following lemma says, if we have a function that is subadditive, f is a function and we require it has two properties. First, as epsilon goes to 0, it goes to 0. Second, it is subadditive. So subadditive means ft plus s is less than ft plus fs. Then we know that in fact, we can take right derivative at 0, and this limit exists and equals the supremum of ft over t. Okay, just before the proof, just a few words. So here we assume that it is subadditive. If we assume it is additive, it means that it equals the right-hand side. And then we already know that combining this and additive, then ft has to be a linear function. And this lemma tells us if we replace additive by subadditive, then around the origin, this guess is still true. It's almost linear. Okay, so why? So we will prove that this limit exists and equals the sup. So we know that the supremums always exist. And clearly, the limit sup is less than a. And we will show that the limit inf is greater than a. To show the limit inf is greater than a, it is sufficient to show that for any delta positive, the limit inf is greater than a minus delta. And then we take delta equals to 0. This shows that the limit inf is greater than a. Since the limit sup is less than a, then we know that the limit exists and is equals a. Okay, so why this is limit inf is greater than a minus delta? The only thing we have is the subadditive. So since a is the sup, and a minus delta is less than the sup, so we know that there exists a t0 such that ft0 is greater than t0 times a minus delta. And then the only condition we can use is the subadditive. So for any t that is small, we assume that t0 equals nt plus u for n integer and u is less than t. So in other words, it means that n is the integer part of t0 over t, and u is t0 minus nt. And then we can use subadditivity. We have the ft plus fu greater than ft0. And then we divide both sides by t0. We have that this is greater than a minus delta. And then we let t goes to 0, or in other words, we let n goes to infinity. So let t goes to 0. Here, for this part, t goes to 0, of course, u goes to 0. And we already assume that as epsilon goes to 0, f goes to 0. So this term goes to 0. And for this term, if we assume t goes to 0, okay, so I just rewrite n over t0 in this form. So as t goes to 0, we can show this one is greater than the limit inf, and this one converge to 1. So as t goes to 0, what we have is the limit inf is greater than a minus delta. So this is what we want. The limit inf is greater than a minus delta, and then let delta goes to 0. Limit inf is greater than a. And this shows that the limit exists and it equals a. So this is the proof of this lemma. And then we can go back to the proof of the theorem. So the theorem says, the first item, this probability, we know that this probability as epsilon goes to 0, it converges to 1. And if we subtract by 1 and normalize by epsilon, the limit exists. And for this first item, we will use this lemma. So we define ft is minus log this probability. And since this is a probability, this pt is a semigroup. And we have multiplicativity of this semigroup. So what we know is pt plus s from x to x. This is greater than pt ptxx times psxx, because this for the left-hand side, it means that we start from x. We jump to x by time t plus s. And for the right-hand side, it means that we start from x. We jump to x at t, and then we jump to x after for another time s. So the right-hand side implies we have the process starts from x, and the n at x is by time t plus s. So at least this probability is less than the left-hand side. And so by this property, we conclude that this f has subadditivity. And in order to say the limit exists, we only need to check f as t goes to 0, it goes to 0. So we only need to look at what happens when t goes to 0. When t goes to 0, we already know that pt goes to 1. So minus log goes to 0. So now we have checked that if we define ft is the minus log ptxx, then it satisfies the two conditions in this lemma. So first, as t goes to 0, it converges to 0. And second, there is subadditivity. So by the lemma we proved, we can conclude that the limit exists. So the limit is this limit exists, and then we can expand this minus log p epsilon, and we see that as epsilon goes to 0, it is approximately the same as 1 minus p epsilon. So this shows the first item. So if p epsilon subtracted by 1, then we can take the right derivative and the limit exists. Okay, and then for the second item, so for distinct states x and y, we want to show that p epsilon xy can take right derivative. So what we will do is, so since p epsilon xx goes to 1, and p epsilon yy goes to 1, then we know that for any c less than 1, there exists a delta such that ptxix and ptyy are close to 1. So for any c less than 1, we know that we can say that for inside a time interval, this probability are very close to 1. And then what we do is we will take epsilon positive, that is very small, such that n times epsilon is still less than delta. So n times epsilon is still in our interval. And we want to compare p n epsilon xy and p epsilon xy. So here what we mean is, so suppose xn is a discrete time Markov chain. With transition matrix p epsilon. Then these two quantities tell us, so p epsilon n epsilon xy is the probability that the Markov chain starts from x and n at y at time n. And this p epsilon is the probability that we start from x and we jump to y within one step. So in fact, epsilon is small and n epsilon is small. We know that both of them are very small because we know that with high probability, the process will stay at x if it starts at x. So compare these two quantities. If we assume that there must be a jump from x to y, then with high probability that the Markov chain stay at x for a long time and then jump to y within one step and then stay at y for a long time until time n. So this is the most likely cases if we want to compare these two probabilities. So now we decompose this event according to where the jump takes place. So this probability is the Markov chain starts from x and arrive at y at time n. And we know that it is greater than if we check where the Markov chain jump from x to y. So if we decompose this event according to where it jumps, suppose it jump at time I. So at time I, it jump from x to y, and then in fact it will stay at y until time n, but we don't write it here. And what is in front is, in fact, we want to say there's no jump before time I. So what we put is, they are not, from 1 to I minus 1, they are not y. So now, in the right-hand side, this event, they are disjoint according to different I. So this is why we have that, we can take out the summation, and then the probability is bounded by the left-hand side. Okay, and then let us consider this term here. So what it says that it's jumped from x to y at time I, and before time I, it never hits y. So by Markov property of this Markov chain, we know that it can be decomposed into 3 parts. The first part is from time 0 to I, and then we jump from x to y. And then we start from y until time, and then we start with y. And at the end, we're still at y. So this is P Okay, so this probability can be decomposed into 3 parts. And this is the term we're interested in, because we want to compare P epsilon xy with Pn epsilon xy. And for this term, it says that because this is a time homogeneous Markov chain, it is equivalent to P n minus I minus 1 epsilon start from y and arrive at y. And by assumption here, we know that this quantity is greater than c, so it's very close to 1. So this term is greater than c. And this is the term we want. So if we put out these 2 terms, what we have is this is greater than c, p epsilon xy times the probability here. Okay, so now we only need to control what is this term. So this term says we start from x. And we arrive at x at time I, and before time I, we never hit y. Okay, we first write this term out. So this equals the probability that start from x and arrive at x at time I, and minus the probability that there exists some jumping at y. So there exists a j. There exists a j such that xj equals y. And for this quantity, by the assumption here, we also know that it is greater than c. And for the second term, it says it starts from x, and it will go back to x at time I, but before these 2 times, there is a jumping to another states. So of course, this is less than the probability that 1 minus will stay there forever. So the second term is less than 1 minus c, because it jumps. So this says this term is greater than 2c minus 1. So here we see that this probability is still very close to 1 when c goes to 1. So we're going back here, what we have is this probability is greater than c times 2c minus 1 p epsilon xy times n. Okay, so now what we have is we compare p n epsilon and p epsilon. What we have is p n epsilon xy is greater than c times 2c minus 1 times p n times n times p epsilon. And now we normalize both sides by n epsilon. So this is the conclusion we have. So now what we have is for any t in this interval and any epsilon small in this interval, and then we take n as the smallest integer of t that is greater than t over epsilon. Then from the conclusion here, what we know is p n epsilon normalized by n epsilon is greater than this constant times here. And then we take epsilon goes to 0. What we have is the left-hand side will converge to pt over t, because n epsilon is the integer such that n epsilon is greater than t, and we have right continuity of the semigroup. So we know that as epsilon goes to 0, this n epsilon goes to t, so this p n epsilon goes to pt. And for here, we can take limit sup. So here we can see that we are pretty close to our final goal, because the left-hand side is the limit sup. The right-hand side is the limit sup, and here it's just a quantity dependent on t. And now we can take t goes to 0 and then take limit inf. So now what we have proved is the limit inf is greater than a constant times the limit sup. And the constant here has nothing to do with this two limits, and we can take c goes to 1. As c goes to 1, this shows the limit inf is greater than limit sup. So this implies that the limit exists and the limit inf equals limit sup. Okay, so this completes the proof of this theorem. So the theorem says, as long as we assume this semigroup is right continuous, then the right derivative exists all the time. So now just let us reorganize with the notation related to this right derivative. So this we call this right derivative as infinitesimal generator of the continuous time process. Yes?
You wanted to prove that it exists, and you also want to prove it's finite?
So here we already know it is finite.
Yeah.
Okay, so just a few words summarizing for the infinitesimal generator. In the previous theorem, we already showed that if the semigroup is right continuous, then we can take right derivative. But the notation we used there is Qx is the limit of 1 minus p epsilon normalized by epsilon. And Qxy is the limit of p epsilon over epsilon. So of course, both of them are non-negative. And now what we want to do is, in fact, we want to take derivative of p according take right derivative at 0. So what we want is we want to define our infinitesimal generator A as the limit that p epsilon minus I normalized by epsilon. So by denoting this, if we denote the entries of A as Qxy, then for distinct xy, this is the same as Qxy here. But if xy are on the diagonal, what we have is Qxx. In fact, it is minus Qx. So it is always non-positive. And moreover, so here in this notation, we want to denote A as the infinitesimal generator. So it is the right derivative of P of the semigroup at time 0. And for this matrix A, what we know is the diagonal term is always negative. And for the term outside the diagonal, it is always positive. And finally, because our matrix is a stochastic matrix, so this still is the summing of 2 is 0. So for this matrix A, we know that if we summing over the whole row, then the summation is 0. So this is also makes sense because when y is not x, then all the terms are positive. And at the diagonal term, it is negative, and the summation of all of them is 0. So this is our infinitesimal generator matrix A. And then we will use this. So first, just a quick example of how to calculate the infinitesimal generator for Markov process. Okay, the first process is the Poisson process. So in the last lecture, we have already shown that if xt is a Poisson process, then it is a Markov chain. So first example, Poisson process. So Poisson process is a continuous time Markov chain, and we also calculate the semigroup. This is the semigroup of this continuous time Markov chain. So now we want to take the right derivative as s goes to 0. So we only look at the first 2 terms of the possible right-hand side. So here we see that if y equals x, so if y equals x, then p as xx, it equals e to the power lambda s. And if y is x plus 1, then this p as xx is e lambda s times lambda s. And if y is greater than x plus 2, then we see that here will be at least s squared. So it's much smaller than s to the power 1. So when we take derivative, then there's nothing. So the limit will be 0. So the only meaningful 2 terms are these 2 terms. And now we take derivative with respect to 0. What we have is Qxx is minus lambda. and then Qx x plus 1. Normalized by S is plus lambda. And for all other terms, the limit existence is 0. So this is the first example. So for Poisson process, the generator of this process A, so this is an infinite matrix. And for the diagonal term, it is minus lambda. And for the term x plus 1, it is plus lambda. And for other entries, they are all 0. So this is the infinitesimal generator for Poisson process. The second example is it's a Markov chain, continuous term Markov chain constructed from discrete term Markov chain. So second example, suppose x hat is a discrete term Markov chain. And NT is an independent Poisson process. And then we define a new process, xt. So it is x hat, take value at NT. So, and in the last lecture, we already showed that this new process xt is a continuous time Markov chain. And for this continuous time Markov chain, in the last lecture, we also calculate the semi-group. So the semi-group is this is the semi-group of this new continuous time Markov chain. And now we want to take derivative at s goes to 0. And here the semi is for all k positive integers. So as if we normalize this semi-group by epsilon to the power 1, then we see that in this term, only the first two terms will have an effect in the limit, and our other terms will become an error term. So we expand this semi-group according to s. So for the first term, we have indicator function on x and y. For the second term, we have lambda s times qxy. And then other terms is just the error term compared to s. And now we want to take derivative. So ps. So when x equals y for the diagonal term, so it's psx minus 1 normalized by s. So what we have is, it is normalized by s. So we take limit. Then we have minus lambda plus lambda q xx. So this is the diagonal term. And for the term outside the diagonal, so for x distinct from y, what we have is qxy equals the limit t as xy normalized by s. So it is the limit of qxy normalized by s. So the limit is lambda qxy. So this is the term outside the diagonal. So here, combining the two, we see that this infinitesimal generator A, we have an expression. So it equals lambda times q minus I. So this is the second example. For the continuous time Markov chain generated by discrete time Markov chain, we know that the infinitesimal generator A is lambda times q minus I. Okay. And then we talk about the relation between infinitesimal generator and the jumping process. So in this theorem, we consider the jumping process. So suppose xt is the continuous time Markov chain we considered. And J1 is the first time that it jumps. And xj1, of course, it says where it jumps. And this theorem says, so in fact, we can calculate the probability, we can calculate the joint law of J1 and xj1. This is the joint distribution. And in this in this formula, we can see that, in fact, J1 and xj1, they are independent. Because this t and y, they have separated distribution. And so this tells us the time we wait until we jump is independent of where we jump to. And from this formula, if we sum it over all y, we can also get the marginal law of J1. So J1 is exponential with parameter qx. This qx is the diagonal term, the minus diagonal term of the infinitesimal generator. And for this xj1, so it says that where we jumps. And the distribution is given by this qxy normalized by qx. So this is, in fact, this is a Markov chain with transition matrix given by this q. Okay, so this is theorem. The theorem tells us. So how to prove this theorem? So the theorem gives us the joint distribution of J1 and xj1. So how to prove the joint law of J1 and xj1? So the proof will be we'll have three steps. First, I will show that this J1 is independent of xj1. So the time is independent on where it jumps. Second, we will derive the law of J1. Third, we derive the law of xj1. Okay, so proof of this theorem. First, why J1 is independent of xj1? So we calculate this event, and we will show that, in fact, this probability equals the probability of J1 greater than T times the probability xJ1 equals Y. And the only property we used here is the Markov property of the Markov chain. So suppose we take conditional expectation with respect to time t. So suppose we know everything happened up to time t. Then J1 greater than t is measurable with respect to this filtration, to this algebra. And for the second part, it's just given everything after time t, we take the conditional expectation of xJ1 equals y. And here what we see is, because we are restricted to this event, so J1 is greater than t, then it means that from time 0 to time t, the Markov chain stays at x and never leaves. So by Markov property, we know that given this part, then the conditional law of this part only depends on what happens for the last step. So it only depends on what happens to xt. And then it is a new Markov chain starting from xt. And now we are calculating the first jump jumps to y. So then it is independent of what happens before time t. So this quantity equals Px xJ1 equals y. So what I say here is this conditional probability equals the probability without conditioning. And then now this quantity is just a constant. We can take out the expectation, take it out of the expectation. What we have is it equals the probability of J1 greater than t times the probability that it is jumping to y at the first jump. This shows that J1 is independent of xJ1. And second, we derive the law of J1. So by the first lecture, we already know that J1 is the holding time. And the holding time has memoryless properties, so J1 has the law of exponential. So suppose that, so we already know that the law of J1 is exponential. So the only thing we need to decide is it is exponential with the parameter Qx, not other parameter. So suppose J1 is exponential with parameter mu. And then we only need to show that this mu equals Qx. So J1 has the law of exponential with parameter mu. So it says that mu is the limit then mu is the limit of this quantity. So here, because J1 has the law of exponential, we know that this event has probability e to the power minus mu epsilon. So 1 minus e to the power minus mu epsilon normalized by epsilon will give us a limit of epsilon. So this is what we already know from the fact that J1 is exponential with parameter mu. And then let us check what is event here. So it says that Markov chain starts from x. The first jumping time is after epsilon. So after epsilon. And we see that it is very close to the probability that the Markov chain starts from x, and at epsilon is still at x. And the difference between these two is just an error term. Because suppose we know this event, then there are two possibilities. The first possibility is J1 greater than epsilon. The second possibility is J1 less than epsilon. Then it means that we have two jumps within time epsilon. So this is an error term with respect to epsilon. Okay, and then by the definition of infinitesimal generator, we know that this term is P epsilon xx. So 1 minus p epsilon xx normalized by epsilon will give us the qx. So this shows that mu equals qx. So this tells us J1 has the law of exponential with parameter qx. And third, we want to derive the law of xj1. So we want to calculate what's the probability that the first jump, the Markov chain for the first jump is jumping to y. So how to calculate this probability? Since we already proved that J1 is independent of xj1, so xj1 equals y. Then this probability equals the conditional probability that given J1 is less than epsilon, because we know that these two random variables are independent. And assuming J1 is less than epsilon, what we know is with high probability that x epsilon equals y. Because if we know that xj1 equals y and j1 less than epsilon, there are two possibilities. One possibility is the Markov chain jumping from x to y before time epsilon, and then it just stays there for a while, so x epsilon is still y. The second possibility is there is another jump before time epsilon, but this means that before time epsilon you have another jump. So this probability will become an error term with respect to epsilon. And then for this conditional probability, what we have is it equals x epsilon equals y over the probability that J1 less than epsilon plus an error term. And for the probability of x epsilon equals y, by definition, it is epsilon xy. And for the denominator, it is J1 less than epsilon, and we know that J1 has law of exponential with parameter qx. So this probability equals 1 minus e to the power minus q epsilon, and then plus an error term. And now let epsilon goes to 0. This term normalized by epsilon will go to qxy. And this term normalized by epsilon will converge to qx. So as epsilon goes to 0, it converges to qxy normalized by qx. Okay, so this shows that the probability of Markov chain starts from x and the first jump to y equals qxy normalized by qx. So here we see that after we define this infinitesimal generator, then we can uniquely identify what's the law of the jumping process. So the jumping process is just a jumping according to this infinitesimal generator qxy normalized by qx. So this tells us, in fact, this jumping process is just a discrete time Markov chain. And the transition matrix is given by this formula. So remark 1. So this theorem tells us the jumping process is a discrete time Markov chain. And the second remark is, in this expression here, we can see that we implicitly use the fact that qx is not 0. So if Qx is 0, then we don't have any meaning in the right-hand side. So what happens when Qx equals 0? So second remark, when Qx equals 0, you can repeat exactly the same proof. So first show that J1 and Xj1 are independent. Second, show that the law of J1 is exponential with parameter Qx. So if Qx equals 0, then what we have is 1. So the probability for J1 is greater than T is 1. So this tells us J1 is infinite almost surely. So this means once we arrive at X, then we will stay there forever. We don't have any jump from there. So in this case, it says that the state X is absorbing. So once we jump to X, then we stay there forever. So this is why that when Qx is 0, we call X is absorbing. So now we have completed this theorem. So first, the theorem is assuming Qx is not 0. Then we have the joint law of this Markov chain, the joint law of jumping time and the jump process given by this right-hand side. When Qx is 0, then in fact what we have is J1 equals infinity almost surely. So this tells us once the Markov chain jumping to X, then it stays there forever. So this X is an absorbing state. Okay, so this is the relation between infinitesimal generator and the jumping process. And now we have a break. We restart at 25. And then we're going to talk about, so what we already know is the right derivative at time 0 equals A. And by multiplicativity, we know that Pt prime equals A times Pt. Roughly, non-rigorously speaking. So suppose Ft is a function, then in fact, from this equation, we can already know that this Pt is e to the power Ta. So suppose that Pt is just a function in T. And in the second part of today's lecture, I will tell you that this idea is roughly true. At least it is true for finite state space, and it is almost true for infinite state space. Okay, so break, and we restart at 25. Okay, we restart. So we continue with infinitesimal generator. So in the previous lecture, what we know is if the semigroup is right continuous, then in fact we know that the right derivative of the process, so it equals Pt times A, because what we already proved is P0 take a right derivative equals A, and this is the infinitesimal generator. And since we know that Pts equals Pt times Ps, so this tells us we can also take derivative for any time t, right derivative. And then the right derivative is Pt times A. And now suppose that this Pt is just a function in t. Then from this expression, from this ODE, we can already solve this, what is the function. So the function should be e to the power Ta. But the only problem here is our Pt is a matrix. A is also a matrix. So this is not just a one-dimensional function. So whether we still can do the same thing. And the conclusion is if the state space is finite, so which means all the matrices here are finite dimensional matrix, then this is still true. So for this part, we first talk about finite state space. And in this part, we first define what is e to the power ta. And then we show that if pt satisfies this relation, then pt equals e to the power ta. So first, what is e to the power ta? Suppose A is a finite dimensional matrix. Then we define e to the power A in the following way. So here in the right-hand side, AK is just a matrix A to the power K, so it's multiplied K times, and then normalized by a constant with summing over all possible K. So for this definition, we know that the right-hand side is still a matrix. And it is well-defined pointwise because this infinite summation has an infinite convergence radius. So for each entry, we know that this is well-defined. So this is a well-defined matrix in the right-hand side. As long as when A is finite dimensional, it is well-defined. And then we define e to the power A as this matrix. So here we see that if A is just a real number, then this is the Taylor expansion of e to the power x. And now we just define e to the power A. A is a matrix in the same way as Taylor expansion. So here we just say that this is the definition of e to the power A. So we define this e to the power, if A is a matrix, we define e to the power A as a new matrix. And then it is defined in the same way as Taylor expansion, just to replace x by the matrix A. Okay, so after this definition, we can first show that some quick property of e to the power A. So consider A is a finite dimensional matrix. And then we define pt as e to the power ta. So this is a matrix. And then this pt satisfies the following three properties. First, there is multiplicativity. Second, the derivative of this pt, so pt is the unique solution to the following equation. Third, pt is also the unique solution Okay, so before we prove what's the difference between the item second and item third, this one, so pt derivative and equals a times pt. Now we put a to the left side. And here is we put a to the right side. So this is what we call the, which one is forward? Okay, so this one is the forward equation, and this one is called the backward equation. So you don't need to remember this two names because I can't remember it. So just the one put a to the left and another one put a to the right. And there is difference between these two equations because since A and PT, they are matrix, there's no guarantee that you can switch the order, they're still the same because now they are matrix. So this is the difference between the second item and the third item. Okay, so why this is true? First, PT plus S. By definition, PT plus S equals exponential T plus SA. And by definition of exponential matrix, This is the definition of e to the power matrix. And then we expand this T and S. And then we replace K by M. This is so just to replace K by M. So we replace K as M plus N. And now here we say that this equals the definition of e to the power TA times e to the power SA. And this shows that PT plus S equals PT times PS. Okay, so this is the first item. Second item. So PT is the solution, the unique solution to this ODE. So what does this solution tell us? Okay, so first we check this PT satisfies this equation. So first, PT is a solution. So in fact, we can prove 2 and 3 at the same time. So first, PT is a solution. Why? Because by definition, PT is e to the power TA e to the power k. So this is definition of PT. And now, since in the right-hand side, this summation has infinite convergence radius, then we can take derivative with respect to t, term by term. So here, we are allowed to take the derivative term by term, also use the fact that the matrix A is a finite dimensional matrix. So if A is an infinite dimensional matrix, we can't do this operation. Okay, so here we say that if we write A to the power k as A times A to the power k minus 1, then this tells us the derivative of PT equals A times PT. And if we write A as A k minus 1 times A, then this tells us PT derivative equals PT times A. Okay, so now this is true just because we have the same matrix A to the power k here. So if it is A times B, then we can't switch the order. Okay, so here we just show that PT is a solution to this equation, and it is also a solution to this equation. And the final piece we need to prove is it is the unique solution. So suppose there is another solution. So suppose PT tutor is another solution. Then since it is a solution, we know that PT derivative equals A times PT tutor. And now we take the product of PT tutor times e to the power minus TA, and then we take derivative. And by the definition, we can show that this equals identity matrix. No, wait. So this equals 0. So you can just expand e to the power minus ta and then take derivative term by term. And you can see that the derivative of the product of these two matrices is 0. So, and then when t equals 0, it starts from identity matrix. So this still is pt tilde equals e to the power ta, if pt tilde is a solution. So this still is pt is the unique solution to the system, to this ODE. Okay, so this is about e to the power ta. And this is some basic property of e to the power ta. And now we can go back to our infinitesimal generator case. So now what we have is, if the state space is finite, then suppose the continuous time Markov chain has generator A, then what we can obtain is our PT semi-group equals e to the power ta. Okay, so the theorem says we already fixed that the state space is finite. And now, suppose xt is a continuous time Markov chain. And the state space is finite. Then the following three conditions are equivalent. First, X has generator A. Second, we know that condition on what happens at time t, then the part before t and the part after t, they are independent. And moreover, we can calculate what's the probability that, so suppose xt equals x, and we can calculate the conditional probability of what happens to xt plus epsilon. So of course, with high probability, if x equals y, so in this expression, we can see that if x equals y, then with high probability, the probability is 1 minus epsilon times qx that at time t plus epsilon, it is still x. But if y is different from x, we know that it's jumping within a small time epsilon, the probability is almost the same as epsilon times qxy. And the third condition is we have this expression. So this expression just says this is a time homogeneous continuous time Markov chain. And where this semi-group PT is the solution to the forward equation. Okay, so before we prove this theorem, this theorem means that these three statements are equivalent. So if X has generator A, then we can show that the semigroup PT is the solution to this forward equation. And by the property of previous lemma, we know that the solution to this forward equation is unique, and it equals e to the power Ta. So this theorem tells us if the continuous time Markov chain has generator A, in fact, we can obtain that PT equals e to the power Ta. So our intuitive is true as long as at least for the state space is finite. Okay, so from item first to item second, this is just definition of the infinitesimal generator. Okay, from first to second. So in fact, this is just the definition of infinitesimal generator, because we know that this conditional probability is p epsilon xy. And by the definition of infinitesimal generator, we know that it equals 1 minus epsilon qx if y equals x. And it equals epsilon qxy if y is different from x. Okay, so from 1 to second, it's just by definition of infinitesimal generator. From second to third, so from second, what we know is, given what happens at time t, the future part and the past part, they are independent. And we have the expression like this. So first of all, for this expression, it is already true, because given this part, we know that this part is independent of what happens to here. So then this conditional probability just equals the conditional probability that if we erase this part. And if we define this conditional probability in this form, the only thing we need to show is this PT is the solution to this forward equation. So from second to third, we only need to show that PT is the solution. So we only need to show that PT satisfies the equation here. Starting from the expansion here, we need to check that PT satisfies the forward equation. So how to check PT satisfies this equation? We need to compare what happens to PT plus epsilon and PT. So PT plus epsilon, it equals the probability that the Markov chain starts from X. And it equals Y at time t plus epsilon. And now we divide this event according to what happens at xt. And then since we know that given xt, the future part and the past are independent, so this probability equals so the conditional probability that x, so maybe I should write it in this way. So here I have done nothing, just take out the probability of xt equals z, and then the remaining part is a conditional expectation, conditional probability. And from the second item, we know that this conditional probability has the expansion like this. And now we write out this, this summation. What we have is, for the first term, it is P so when z equals y, we have a txy. And for z is distinct from y, what we have is ptxz times epsilon qzy and plus an error term. So here, just note that this error term is inside this summation. And now, since our state space is finite, so when we take it out, after summing, it is still a small term with respect to epsilon. So from here to here, we use the fact that the state space is finite. So if it is infinite, then it is not true. Okay, so now, since we have this expression, now we can take derivative. Okay, I just want to emphasize that from here to here, we use the fact that the state space is finite. Otherwise, it is not true. And now we can take derivative. So what we have is pt plus epsilon xy minus ptxy normalized by epsilon normalized by epsilon, it equals z ptxz times qzy plus an error term. And we can also compare pt minus epsilon and pt in a similar way. And we will get a similar expression as here. So then we take epsilon goes to 0. What we have is ptxy equals pt times a xy. So this tells us the semigroup PT satisfies this forward equation. And from the previous lemma, we know that e to the power ta is the unique solution to the forward equation. So then PT has to equals e to the power ta. Okay, so this is what happens to the finite state space case. So then we know that the semigroup, in fact, it equals e to the power ta. But here we say that the proof highly depends on the fact that the state space is finite. So the conclusion is not true for infinite state space. So next, we look at what happens to infinite state space. For the infinite state space, so countable infinite state space, if xt is a continuous time Markov chain with generator A, then we know that this pt is the minimal non-negative solution to the backward equation. Okay, so for countable infinite state space, then the conclusion is if xt is a continuous time Markov chain, with generator A, then the semigroup PT is the minimal non-negative solution to the backward equation. No. Okay, so there are several pieces of the information. So in this theorem, it says that first, PT is a solution to the backward equation. Second, it is the unique minimal non-negative solution. So roughly speaking, so from this theorem, what is still true is, given A, we can uniquely determine what is the semigroup. This is the same as the finite state space case, because we know that this PT is the minimal non-negative solution to this backward equation. But what is no longer true is now we can't write PT as e to the power TA. So this theorem tells us, given generator A, we can uniquely determine what is PT. So PT is the minimal non-negative solution to this backward equation. So this theorem has two parts. First, we need to show that PT is a solution. Second, we need to show that PT is the minimal non-negative solution. So what does this mean? It means that if we have another non-negative solution, then we always have PT tilde is greater than PT. So this is the meaning that PT is the minimal non-negative solution. So if PT tilde is another non-negative solution, then it is always greater than PT. So this is the two conclusions contained in the theorem. Okay, so we first prove that PT is a solution. And the only information we have is the generator is A. So first, PT is a solution. So PTXY is the probability that it starts from X and then jumping to Y at time T. And now we divide this event according to what happens to xj1. So divide according to what happens to xj1. So the first possibility is j1 happens after t. And then j1 happens before t. So j1 happens before t, and now we divide according to where it jumps at the first step. So divide the event according to where it jumps at xj1. So z has to be distinct from x because we know there is a jump. This is a real jump, so it has to jump to another vertex. And then xt equals y. So now we calculate these two parts separately. For the first part, so j1 happens after t. Then it means that xt should equals x. And then now we use xt equals y, so this is only possible when y equals x. And when y equals x, now we are just calculating the probability that j1 is greater than t. And we know that the j1 has the law of exponential parameter with parameter qx. So this part equals qxt. So this is the first part. And then for the second part, so what we have is, we know what is the joint law of j1 and xj1. So we already derived the joint law. And now we just write out the probability with respect to the joint law. So the density for j1 is exponential with parameter qx. So this is the density for j1. And the jumping probability for xj1 is qxz over qx. And then for the last part, what we have is starting from z, we arrive at y at time t minus u. So from here to here, we first decompose this event according to the joint law. And then by Markov property, the conditional probability of xt equals y, given what happens to j1 and xj1, just equals pt minus u, jumping from z to y. Okay, so from this expression, what we have is ptxy equals qxz So we have this equality for all xy. And now we multiply both sides by e to the power tx. So we multiply both sides by e to the power qxt. And now here will become qx times t minus u. And here is also t minus u. So now we change the parameter. Okay, sorry. U by t minus u, what we have is and now we can take derivative to both sides. Then the left-hand side become so now in fact we are taking the right take the right derivative. This is the left-hand side. And for the right-hand side, so here, so we have an infinite summation here and we have an integral, but all the quantity here are non-negative. So by Mandelton convergence theorem, we can switch the order of summation and integral. And after we switch this integral outside, now we can take right derivative. So this is the derivative of the right-hand side. And now we erase e to the power qxt. What we have is qx ptxy plus pt prime xy ptxx. Sorry. Yes. ptxy. And now we remove this term to the right-hand side. What we have is PT derivative equals Z QXZ PTZY. And here we use the fact that QXX equals minus QX. So here this tells us PT prime equals A times PT. So this proves the first step. So PT is the solution to the backward equation. And now we prove the second step. So the second step says PT tuta, if PT tuta is another non-negative solution, then we always have PT tuta is greater than PT. So since PT tuta is a solution, so now we reverse the procedure from here to the top line in this part. What we have is, since PT tuta is a solution, we must have PT tuta equals So here, what I have done is I reversed all the procedure here until here. So suppose PT tuta is a solution, then we must have PT tuta satisfy the equation here. Is there any question? Okay, and then we can compare what happens to PT tuta and the PT. So we will prove by induction that the probability of xt equals y, t before jn, is less than PT tuta. And just a remark that after we prove this conclusion, then as n goes to infinity, jn goes to infinity, because we are under the assumption that there's no explosion. So then the left-hand side will converge to PTXY. So this completes the proof. It shows that PTXY is always less than PT tuta. Okay, so for this claim, we prove by induction. First, when n equals 1, the left-hand side equals Px xt equals y, t less than j1. Since t less than j1, it means that xt equals x. So this is only possible when x equals y. And when x equals y, we're just calculating the probability that j1 is greater than t. And we know that j1 has the law of exponential with parameter qx. So this probability is e to the power minus qxt. And then by star, since PT tuta is non-negative, we know that the second term here is non-negative. So PT tuta is greater than the term here. So by star, and the fact that PT tuta is non-negative, we know that this is less than PT tuta xy. So the claim is true for n equals 1. And second, suppose the claim is true for n. It is true for n. And then let us consider what happens to n plus 1. So what happens to n plus 1? So we want to show that, assuming the conclusion is true for n, we want to show that for n plus 1, this probability is also less than pt tilde. And now, for this event, we divide it according to what happens to J1. Divide according to what happens to J1 and xJ1. So what we have is the first possibility is J1 greater than T. And J, okay. So yes, the first possibility is J1 greater than T. And the second possibility is J1 less than T. And then I divide the event according to where is xj1. Okay, and again, for the first term, what we have is this probability is e to the power minus qxt. And then for the second term, we do the same thing. We divide this event according to the joint law of J1 and xJ1. Okay, so here what we have is, because this is a Markov chain, so given what happens before time u, then we know that this is a new Markov chain starting from z. And now we want to calculate the conditional probability that xt equals y and t less than jm plus 1. So now we already know that the first jump happens at time u. And then this jm minus 1, the jm plus 1 becomes the jump for the new process at time n. So it's just the nth jump for the new process. So we have this quantity equals times pz xt minus u equals y and t minus u less than jn for the new process. And then for this probability by assumption, so by induction hypothesis, we know that this probability is bounded by p tilde. So here is we use the induction hypothesis. And again, by this expression star, we know that this equals pt tilde xy. So from here, we prove the conclusion. So the conclusion is true. So now what we have is, for any n, the probability of xt equals y and t less than jn is bounded by p tilde. And now let n goes to infinity. And since we restrict to the non-explosion case, then the left-hand side converges to ptxy. So this shows that ptxy is bounded by pt tilde. So this completes the proof. So in this theorem, what we have is the infinitesimal generator A still uniquely determines the semigroup, and the semigroup is the minimal non-negative solution to this backward equation. So although we can't say that pt equals e to the power ta, but we still know that given A, then this pt is uniquely determined and through this process. Okay, is there any question? Okay, if there's no question, I will talk about the two models and then talk about how to calculate the infinitesimal generator for these two models. The first model is called MM1Q. Do you have any question? Huh? Ah, okay. Okay, the first model is called MM1Q. So this model describes a service system. So suppose customers arrive according to a Poisson process of intensity lambda. So customers arrive according to a Poisson process of intensity lambda. And now we have a single server. And for this single server to serve the customer, and the server's time is IID exponential. It's IID exponential with parameter mu. So what means is, so suppose after time exponential lambda, so we have a server here. And after time exponential with parameter lambda, the first customer arrives. And when it arrives, the server will serve the customer. And the service time is an exponential with parameter mu. And if before it finished the service of the first customer, then there may arrive a second customer because the time difference is just exponential with parameter lambda. And then the second customer has to wait until the first customer leaves, and then the server serves the second customer. So this is the system, and it is called MM1Q. So there are two parameters. One parameter lambda tells how frequently the customers arrived, and the second parameter mu tells how fast the server gives the service. And then we denote xt as the length of the queue. So this is the length of the queue at time t. And now we are interested about this process xt. So first, we can see that this process xt is a continuous time Markov chain. And we can also calculate the infinitesimal generator. So I will give you 3 minutes on this model. So first, quick check why this is a continuous time Markov chain. So understand this model and try to solve what is the infinitesimal generator of this process. Okay, so first, this process xt, we want to explain that it is a continuous time Markov chain. So why this is true? Suppose we fix the time t, and then we know what happens after time t. Then we look at what happens to the future. So what happens is the customer arrives according to a Poisson process of intensity lambda. So the jumping times, so the arriving time difference is just exponential with parameter lambda. And another information we have is the server gives the service, and the service time is the IID exponential. So, and we know that for the exponential random variable, we have memoryless property. So knowing what happens after time t, then the new process then what happens in the future is just a new process. Start with xt customers in the queue, and then the service time is still IID with exponential is still IID with exponential of parameter mu, and the new customers arrive still according to the Poisson process of the intensity lambda. So this roughly tells us this is a continuous time Markov chain. Homogeneous continuous time Markov chain. And in fact, we can calculate explicitly what is the conditional probability of given xt, what's the conditional probability of xt plus s equals n. So this will be done in the recitation of the next week. So in fact, we can calculate explicitly what is this PSMN. So after we know what is the expression for PS, then we can calculate what's the generator. So today I just want to tell you, before we know what is the exact expression of PS, we can still know what is generator. So what does generator mean? So generator says so the generator just gives us the estimate of this probability. So we start with m customer in the queue. And after time epsilon, there are n customer. And then we want to epsilon goes to 0. And we just want to calculate what is the derivative when we calculate the infinitesimal generator. So as epsilon very small, we can imagine that in this small interval, from time 0 to epsilon, with a high probability that there's no customer arrive and that the previous customer doesn't leave, because we know that the service time is exponential with parameter mu. So with high probability that we should have n equals m. So with high probability, n equals m. And then with probability lambda times epsilon that we have a new customer in this interval. So a new customer arriving in this interval, and this probability epsilon times lambda. And in this case, what we have is n equals m plus 1. And there's also a small probability, which is almost the same as epsilon mu, such that one customer leaves within this interval. And then this corresponds to n equals m minus 1. And of course, you can also say that it is possible that one customer arrive and one customer leave within this small interval. But then the probability will be much smaller than epsilon to the power 1. It will be epsilon to the power 2. So when we take derivative, we don't care about higher order of events. So what do we have from this analysis? What do we know is, so in fact, we have that the infinitesimal generator QMM. So this corresponds to the derivative of QMM. And this corresponds to the derivative QM m plus 1. So we know that it equals lambda in this case. And this corresponds to QM m minus 1. And in this case, the derivative equals mu. And in the first case, it is minus lambda minus mu. So before we calculate explicitly what is this PS mn, we already know that what is the generator of the continuous process. The only point we need to take here is, so here in fact we assume m is greater than 1. So if m is 0, there is a difference. So if m is 0, so what happens? So m is 0 means there's no customer at time 0. And within this epsilon interval, it is with probability epsilon lambda that there is a new customer. And since there's no customer before, so the customer can't decrease. So what this tells us, if m is 0, then Q01 is lambda, and Q00 is just minus lambda. So this is how we get the generator of this MM1Q. And more will be discussed for this M1Q in the last lecture's recitation. Okay, is there any question? Okay, the second model is called MM infinity Q. So this 1 corresponds to single server. This infinity means we have infinitely many servers. So MM infinity Q, it means that so the customer still arrive according to a Poisson process with intensity lambda. And now suppose we have infinitely many servers. And the service time is still IID with exponential mu. And then xt is the length of the queue. Length of the queue at time t. And we want to ask what happens to this process xt. So first, this is a continuous time Markov chain. And we can also calculate the generator. So 3 minutes on understanding this model. So this model, the difference between this MM infinity queue and MM1 queue is now we have infinitely many servers. So this means that once the customer arrives, it will be served immediately. So the customer don't need to wait. So as long as once he arrives, then the server, a new server will serve him. So he doesn't need to wait. And this means xt. This is the length of the queue. In fact, this xt just means how many servers are serving at time t. So because no one is waiting, everyone is served. Okay, so for this model, it is a continuous time Markov chain. And in fact, we can also calculate explicitly what is PSNN. So this will be done in the next next Monday. And in fact, a key point here is before we calculate the generator, we have to argue that there is no explosion. So although the process, the other conclusions I considered during my lecture is for non-explosive Markov chain, but now I give you a new Markov chain. I didn't say anything. So first, you have to show there is no explosive. There is no explosion. And then this is so after we knowing that this is a continuous time Markov chain and there is no explosion, and now we can consider what happens to the infinitesimal generator. So for the infinitesimal generator, we want to evaluate the probability of p epsilon mn. So what happens in the time interval 0 epsilon? So with a high probability that in this time interval, nothing happens. So no one arrives, no one leaves. And then in this interval, we know that with probability proportional to epsilon lambda, there arrive a new customer. So arrive a new customer. And then it is also possible that there is customer leave the queue in this time interval. So there is one customer leave the system. So then what's the probability that it happens within this interval? So suppose we have one single server. So if we just have a single server, we know that in this time interval with probability epsilon times mu, one customer will leave. But now we have infinitely many servers, so which means all this m customer all of the m customers, they are being served at time in this time interval. So then, at least one of them leave the system. The probability become epsilon mu times m. So this is the probability that within this time interval, there exists one customer leave the system. Of course, there's also other possibilities, and then all of them will have probability that is smaller than epsilon to power 1. Okay, so then this tells us the infinitesimal generator in this case is m plus 1 equals lambda. And this tells us q m minus 1 equals m times mu. And this tells us q m equals minus lambda minus m mu. So this is the infinitesimal generator for infinity q. And then, just the same as before, we need to take care of what happens to m equals 0. So for m equals 0, we know that it is possible to have one new customer, but it's impossible to have one less customer. So what we have is when m equals 0, q01 equals lambda, and q00 equals minus lambda. So this is the generator of the infinity q. Okay, and I will stop here for today. And in the next Monday, there is no lecture, so all 3 classes are recitation, and it will meet various models and see how to prove that they are continuous time Markov chain. There's no explosion, and how to calculate the transition semigroup, and how to calculate the infinitesimal generator. Okay.